First speaker today. So our first speaker is our very own Dr. Romane Le Gal. Romane's research focuses on the chemical evolution of interstellar matter from prestellar environments through the protostellar stages to the formation of planetary systems. Romane completed her undergraduate education in Paris and Grenoble before pursuing her PhD at the University of Grenoble. And following this, Romane moved to the US to undertake a postdoc at the University of Virginia, and then joined the CfA in 2017 to work with Professor Karen Oberg's group. And the title of her talk today is Probing the Chemistry of Proto-Planetary Disks and its Impact on Planetary Systems Composition. Romane, please go ahead.
Yeah, okay. Thank you, James. So can you all see my screen?
We can.
And I'm just going to, because I can't, so here now, better, okay. So yes, so as James said, so I'm a postdoctoral fellow in Karen Oberg group at the CfA. And so, yes, so I'm going to present you today some recent studies that we performed to probe the chemistry of protoplanetary disks and its impact on the planetary system composition. So as an introduction here, I have depicted a schematic view of a protoplanetary disk that is seen edge-on, and where I have depicted, where is depicted here the solid and gaseous phases that we can now probe thanks to the last generation of telescopes. So you have, for instance, the distribution in dust and the different size of this dust in disks that are seen. The ice line, the major ice line. Oh, sorry, there is one missing word here, but this is the limit of the water ice line, and here the CO ice line that are happening in disks. Also, we have some planets that are depicted here in order to emphasize that this is in this disk that planets are forming and that they can impact the disk interior and the disk chemistry of this disk. And we have also access to the gas phase of this disk. And so here I have depicted images that were taken with ALMA mainly. So during the past 5 years, mostly, and where we see some of the major species that are detected in disks. So with CS, formaldehyde, small organic, and C2H. And each of these molecules is probing a different region in disks, and also is observed at, is supposed to trace a different layer in your disk. So this can give us a lot of information, not only on the chemistry, but also on the physics that is occurring in these disks. But even if we have all access today at this wealth of observation, there is still a lot to understand about the formation and the evolution of this protoplanetary disk. And in particular, we still don't know, for instance, what are the initial conditions of such protoplanetary disks. So in particular, their molecular contents, so their molecular composition, but also their elemental budget. So in carbon, nitrogen, oxygen, sulfur, and phosphor, which are the 5 more important elements for planet buildings. We also don't know what is the balance between chemical reprocessing that can occur in situ, so in this disk, and versus the chemistry that is inherited from preceding evolutionary stages, so inherited from the interstellar medium. And last but not least, we also don't know if and how planet formation can impact the chemistry of their disk, and if so, if we can identify chemical signatures of planet formations. So these are 3 main questions that we are interested in probing.
No, I'll do without them till you finish.
So, but in order to do that, so we have the observation. So here, oh, sorry, are you asking a question, Irvin? Okay. Okay, sorry. I think you're muted, Irvin, now. Okay, so I keep going, James? Yeah, okay. So yes, so we have not only the observations, and so in particular, so here, so we are currently working on a large program that has been performed with ALMA, which is called MAPS for molecule with ALMA at planet forming scales, and for which Karin Oberg is the PI. And so this is a wealth of data that concerns 5 disks mainly that we were able to probe very deep in chemistry. And so the results should be out soon, but nothing here yet. Nothing in the poster yet, still under embargo for most of the data. But you will hear about this soon, I'm sure. But so in order to understand the chemistry of disk, so we need to constrain the chemical network that are linking all the species that we observed. And so for that, we build a chemical network such as the one I'm just depicting here. So here I'm focusing on sulfur. So why sulfur? So sulfur is a very intriguing element, not only in disks, but also in the interstellar medium that has been, this has been the case for more than 20 years. But during the 5 past years, we were able to detect a lot of sulfur-bearing species in different interstellar environments, which are helpful to build, to constrain the chemical network of sulfur, not only for the interstellar medium, but also for disks, because we think that most of the chemistry is inherited. So here I have depicted, so the 12 blue ellipses are the sulfur species detected in prestellar cores. So the black one are the ones that are also detected in photodissociation regions. So photodissociation region are the region in interstellar medium that are the interface between diffuse and molecular and dense interstellar medium, where there is a lot of UV photon impact on the chemistry. And the yellow stars here depicted the sulfur species that are being observed in a protostellar envelope, so in which a disk will form later. So it's just to show you that all these species are connected and they are observed in different kind of interstellar environments. So we are building the chemical reaction, and I mean working with chemists that help us to constrain the chemical reaction that links all these species, and where you have different reactions that are occurring either in the gas phase or on solid states, so on grains and on ices that are wrapping grains. And so from this chemical network that we built, then we can run astrochemical models, and in particular astrochemical models for disk studies. So this is what I've been doing last year, and I'm still doing that in the group of Karin in order to constrain the chemistry of disks. And in particular, to understand the sulfur species that are observed in disks. So in disks, so far, we only have 4 species that contain sulfur that have been detected, CS, SO, H2S, and H2CS. And H2CS, we only detected this species last year, so we reported the detection, the first detection of H2CS in a disk last year only. So this was thanks to ALMA that we were able to perform such observations. So this was very exciting. And so with ALMA, we detected a lot of interesting structure in CS. in 6 different disks. So here I'm showing the spatial distribution of CS in one disk, mainly, where we see that we are able to distinguish gaps and rings in CS. And so with my models that are built from my previous chemical network of sulfur that I built previously for interstellar medium studies, I implemented this network in disk astrochemical model that I developed, so 2D disk astrochemical model that is seen edge-on here. And so we are able to reproduce the spatial distribution, but also the abundances of the species that are observed in disk for CS. So this was very exciting. And we were able also to predict what should be the abundances for the 3 other species, H2CS, H2S, and SO, that are now detected in disk, but others disk. So we need really more observation of sulfur species in disk to really be able to better constrain the chemistry of the sulfur species in such disk. And so in particular, planets from disk are stratified. So they are stratified mainly in 3 layers. So for instance, if you took here this schematic view that I made of a disk, you have the very atmospheric layers that is can be compared as a photodissociation region, then a molecular rich layer that can be analogous of a molecular cloud, and then the mid-plane, which is very rich in dust, and where most of the species are frozen onto this dust. And that can be analogous to very dense cloud cores, so such as prestellar cores. And so the idea is really to understand if the chemistry in disks resemble more that of photodissociation region. So are we probing really, I mean, mostly the atmospheric part of disk, or are we probing more shielded, or are disks more similar to shielded ISM environment, and can we probe a deeper layer in the disk? And so to further investigate this comparison, so I did a benchmark between a photodissociation region, so a classic one, very well-studied one, the Orsted photodissociation region that is seen edge-on, and where you have 2 positions that have been deeply studied in the past in radio astronomy. So you have a position that is really a photodissociation region, and an inner position, so the core position that is the analogous to a more dense dense cloud core regions. And so in this PDR, we had, so in the Orsted Nebula, we had observation of methyl cyanide, which is a very interesting species because it has been also observed in disk. And this CN bond is a very important bond for prebiotic chemistry. So it's also of very much importance for then the hospitability of planets for life. So we studied the CH3CN observation that we had in a PDR. And so for that, I built a PDR model. So for that, I extended, so I built the chemistry of this model using a famous PDR code model. And I did the same for disks. So with my disk model, so it's an independent different model, in order to reproduce the CH3CN that was observed in disk. And so the main takeaway from these models are that in order to reproduce the CH3CN in both PDRs and protoplanetary disk, we need a C/O ratio that is higher than the sun value in both types of objects. So does this mean that maybe it means that CH3CN is mainly probing the atmospheric layers of disk, and so that we can have protoplanetary disks that are more analogous to photodissociation regions. But another interesting point from this model is that in order to reproduce the CH3CN that was observed in the very inner part of the Orsted Nebula, in the core region, we only, we need a lower C/O ratio, so not unity, still a bit higher than the solar one, but lower than the one that is observed in the external region, so the photodissociation region. So this is why now we would like to be able to probe other layers in disks, and probably for that we need other type of observation. And so we hope that with the James Webb in particular, we'll be able to probe different disk regions, so different disk layers, probably more the inner part of disks, where you can have a different chemistry, but also to go deeper in the disk and be able to really probe the mid-plane layers of disk, where the chemistry is frozen onto dust, and maybe we'll have more constraint from this observation on the chemistry of disks, and so how they are inherited and how they are reprocessed also in disk, and what is their what are they going to become, and how are they going to be spread onto the planets that are forming within those disks. And I think I can stop here, probably. I've been long enough.
Thanks, Romane. Very interesting talk. Do we have any questions? If so, please raise your hand in the participants window. Oh, Erwin, you have a question, I can see. Go ahead. You're muted at the moment. You're muted. Your microphone is muted. You're still muted. Nope, I still don't hear you. Perhaps if you could also type your question into the chat, and I can read it out for you. Does anyone else have a question while Erwin's doing that?
Now you can hear me, right?
Yep, now we can hear you. Yeah.
Sorry. On this slide that's on the screen, no, when you go from the top first and then the second, there's a complicated interplay of all these interactions between all these molecules and so forth. Very complicated. What I was curious about is, do we know anything about the rates of the interactions indicated here and how they depend on pressure and temperature and things like that? What's the state of the art there?
Yes, that's a very important question indeed, because so this is why we really need to closely work with chemists in order to constrain those rates. And so as of today, I mean, there are approximately only 10% here of the rates that are constrained either theoretically or experimentally by chemists. But the other 90% are mostly guess rates that were estimated from similar type of reactions, but there is still a lot of work to do. But for the one that are constrained, yes, they vary for some of them with the temperature. And so here also to remind that the chemistry is a bit different. I mean, I think that most of the audience is more used to atmospheric exoplanet atmospheric planet chemistry. And so here we are really dealing with different type of chemistry, because the density, I mean, it's much more less dense than what you would have in an atmosphere, and the pressure also are much more low. The same for the temperature. So the chemistry is very different. And for instance, we don't have three-body reactions in the gas phase that can occur in the ISM, because I mean, it's unlikely that this can happen. So it's only bimolecular reactions or associative reactions or electronic recombination with electrons. But the chemistry is very different than the one that you can have in atmosphere because of the physical condition mainly. So, but yes, yeah, to answer even to your question, yeah, it's only 10% that are constraints so far. So we still need to closely work with chemists.
Thank you.
Any other questions for Roman? Okay, then thank you very much, Roman. And we'll move on to our second speaker today. So Suri, please go ahead and introduce our second speaker.
All right, so our second speaker is Jayesh Goyal. He did his master degree in atmospheric science from Indian Institute of Science in Bangalore. Then he moved to the UK to do his PhD at the University of Exeter. He's currently a research associate at the Department of Astronomy, Cornell Arts and Science. And today, he's going to tell us about a library of simulated exoplanet atmospheres and spectra. So please go ahead, Jayesh. You are muted and not sharing.
Yes, I'll just share my screen. Are you able to see the screen?
Yep.
Okay. And you're seeing it the first section of the slide, I guess.
Yes.
Okay. Thank you. Thank you for the introduction, Suri. And thanks, Romane, for that talk to proceed to this part. So Romane talked about the initial version of the proto-planetary disk. And after that, we'll now move to like exoplanet atmospheres, a bit more ahead in time. And how do we find what's going on there? What are the atmospheres of these planets are like? So that is what I'm going to focus on mainly in this talk. So in like last 10 to 15 years, we have getting a lot of observations of exoplanet atmospheres. There are very few planets that we have able to observe in details. And in the future, like with JWST, we are going to get more observations. So to understand this observation, we need theoretical models. Like we need to model the atmospheres. Now, the atmospheric modeling of different planets can be very complicated because there is chemistry, there is dynamics of the atmosphere. So many things are involved. Like just looking at the weather and climate prediction on Earth, we can understand how difficult the atmospheric modeling is. And basically, so for atmospheric studies of exoplanet, we have to combine our atmospheric studies of the Earth and planetary science with the astrophysics and understand the observations that we are seeing. So, that was our aim in developing a library of models to interpret this observation that we have started getting. And this is what I'm going to focus on my talk. So the first, most of the observations that we get for exoplanet atmosphere currently are through transmission spectroscopy and emission spectroscopy. So in the figure here, you can see when the planet orbits around its host star, in the primary eclipse, that is the transmission spectroscopy, we probe the limb of the planetary atmosphere. So in that is like day-night boundary. So we get information of this part. So when we get the transmission spectra, we need to model this part of the atmosphere to compare with the observation and understand which molecular species are present, what is the temperature there, are there in haze or clouds. So that's the first part. And then in the emission spectroscopy, when the planet goes behind the star, so just when it goes behind the star, you take the planet plus stellar signal. And when the planet goes behind the star, you just get the stellar signal. And you subtract the stellar signal from planet plus star signal. So that is how you get the planetary signal. That is, and in this case, we are assuming here, like most of these planets that we are looking at are hot Jupiters and very close. So they are mostly tidally locked. So what the information that you get is from the day side of the planetary atmosphere. That's why you can see in the plot, we have this side, the red color area is the day side of the planetary atmosphere. So in transmission spectroscopy, you're getting day-night boundary, and in emission spectroscopy, you are getting the entire day side. And also on the right hand side, there's a figure. In transmission spectroscopy, you are probing a very thin part of the atmosphere, quite high. It is because the rays of the radiation are going through the limb. So you have to go through a large part of the atmosphere. So the atmosphere becomes opaque and you can't probe much deeper because it will be like all absorbed. But in emission spectroscopy, you are actually probing in the radial direction from the planet. So you have to just go through the width of the atmosphere. So in that case, you can probe much deeper in the atmosphere. So in the emission spectra, you can see here in the plot, we can probe much deeper. In transmission, we can't. So that's why both of these techniques are analogous. Like for transmission, you can get day-night boundary and a small upper part of the atmosphere. But in emission spectra, you can go deeper and get the day-night side of the atmosphere. And from the observational perspective, transmission spectroscopy is easier to do because you get high signal to noise ratio, at least with the current Hubble Space Telescope observation. With JWST, this might change. And in emission spectroscopy, it is very difficult to get because you are getting the photons in the infrared and already the noise is bigger. So it becomes observationally challenging to do emission spectroscopy. So you might notice in the field also, the emission spectra has been obtained only for very few planets, and that too for mainly ultra-hot Jupiters. But transmission spectroscopy we have done for many, like around like 40 to 50 of exoplanets, we can say. So what we have done is so we select in our initial work, we selected around 117 planets. We thought were good for transmission spectroscopy based on their scale height, which is governed by the temperature and the temperature and gravity. And we developed a library of models for them. And this library of models are basically used to plan and interpret the observation and also identify large-scale statistical trends, which we can do for some of the planets where we have more observations now. And also the most important thing is these are forward models. So you can plan the observation always. Also, these observations of atmospheres have a lot of physical processes going on. There is condensation, there are winds, there are clouds, haze, different molecular species. All these are combined together to give their effect on the spectra. So how do you decouple them effect? Like there are a lot of degeneracies. So this is what the grid of forward model help us there. So when we develop this grid, we vary each parameter at a time, and that helps us to decouple the effect of each and of the parameters on the spectrum. So in our first work, what we did is we developed. You can see here on the left hand side there like the spectra. Like a lot of transmission spectra. This is in the day-night boundary, the transmission spectra. So this plot is like on the y-axis there is transit depth, and on the x-axis it is wavelength. And we are this is done for equilibrium temperature. So based on the distance of the planet from the host star, we have generated these models for different equilibrium temperatures of the planet. Then atmospheric metallicity. So metallicity is basically governing the chemistry of the atmosphere. Like if you increase the metallicity, basically you're deviating from hydrogen helium dominance. So if you are at solar metallicity is hydrogen helium dominated, but as you start moving towards higher metallicity, the heavy gases or heavy elements become higher in the atmosphere. Their abundance increases. So for that's why when you look at the equilibrium temperature, you can see the 600 Kelvin, this particular one, it is dominated by methane. Methane, because at lower temperatures, and this is on equilibrium chemistry. We are assuming equilibrium chemistry because we have to assume something. We don't know what is in this planets. We have starting with something. So and equilibrium chemistry is a good assumption because these are very hot planets, and for hot planets, the reaction rates are, you can say like it's quite fast, and you can reach a state of equilibrium. So that is a good assumption to start with. So so that's why, according to equilibrium chemistry, we predict at lower temperatures the planets should have methane features. So a lot of methane features you can see around, and also phosphine. You might have phosphine, which we recently there is a claim to be detected in Venus. So such things can happen at lower temperatures. Then as you go to increasing temperatures, you see it is dominated by different species. Like first you come, there is CO2, carbon dioxide, carbon monoxide, and water. Now as you start going from lower temperature to high temperature, the most prominent is the shift from a methane dominated spectrum to a water dominated spectrum. So that at higher temperature you expect water features to be dominant, and at lower temperature you expect methane to be dominated. And here we are showing the spectra for two different condensation regimes, that is local condensation and Raynaud condensation. What does this mean? So we don't know for exoplanets what kind of condensation takes place. So when I say local condensation, it means that the abundance of a particular species is just dependent on the local temperature and pressure of the layer of the atmosphere. That is what the local condensation means. But in the Raynaud condensation, what I mean is it depends on the previous layers, like how is the pressure, temperature, structure of the atmosphere. So depending on what species were condensed lower in the atmosphere, the abundance of the species higher in the atmosphere will be controlled by that. So that is what. So that's why when we develop this grid of models, we develop it for both of this condensation. And you can clearly see there are differences here, especially here. If you see at a 1500 Kelvin model, in a Raynaud condensation, you have sodium and potassium features, while for local condensation, you have titanium oxide and vanadium oxide features. So these are the two different things which are expected. We don't know which of this is common. So when we study, when we get more observation, we might be able to constrain this. So this is for equilibrium temperature. For metallicity also similar things can happen, like different features. As you go from like solar metallicity to 200 times solar, you can see the features are changing. You have CO2, SO2 at 200 times solar. Then also in the Raynaud and local condensation, you see the differences. You have sodium and potassium on the Raynaud condensation, while here we have a VO. And as Roman earlier talked about the C2O ratio, the C2O ratio has implications here also. So in the lower part, I show like how the C2O ratio affects the spectrum. So as you go from low C2O ratio to a high C2O ratio, as expected, the carbon dominated species like CH4, HCN, they will increase in the atmosphere, and that's why you can see their spectral feature. So that is what this library of models, they have like all the various. So this is around like more than 36 to 40,000 models we have generated, which can be used by observers, everyone for JWST and any other telescope to interpret their observation or plan their observation. Then we have also included the effect of haze and clouds. Now, when I say haze and cloud, this is very simplistic. So this is a Rayleigh scattering haze. You can see here this slope, like lambda to the power -4 slope. And as you increase the amount of haze in the atmosphere, the size of the features get decreases. So this is one of the questions which is unanswered in atmospheric for exoplanet atmospheres, is like the water features. There is a 1.4 micron feature. The water feature that we are seeing for many of the planets is smaller than expected for a clear atmosphere. And we don't know why. So it might be haze or it might be clouds. When I say clouds, it's like a gray cloud. So it's like it decreases the size of the feature, but it makes the spectrum tends towards making the spectrum flat as opposed to the Rayleigh scattering haze. So both of these things can make the water features less, but we are not sure which was. So currently we are just understanding that thing. So in this work, what we did is we did sensitivity analysis for all these parameters that affect the transmission spectra. We identified different chemical regimes. Like one regime we observed was like, if you can see here at 1500 Kelvin, like in one of the hot Jupiter planets, there are chemical regimes where vanadium oxide can exist without titanium oxide. All these small and integrated details we were able to identify in this sensitivity analysis. And one more thing, so like the grid that we generated, the second grid that we generated, we generalized it for a variety of temperature and metallicity, so it can be scaled to any hydrogen helium dominated atmosphere. And in our paper we have derived this relationship which people can use to do that. And this is also this grid is available publicly on ExoCTK, the Space Telescope Science Institute ExoCTK portal, so anyone can use it, all the observers and model people. So after this, once we did that, the starting step for transmission spectra. So next step was actually going towards a more complicated stuff. Now in the first grid, we were probing a very small part of the atmosphere, as I show here. So so that's why we use isothermal pressure temperature structure in that case, which was all right. We tested this with the current observation. But in the next step, we have to do it physically consistently. And also, if you want to generate emission spectrum, you want to like get the thermal structure of the atmosphere, we need to calculate that for emission spectrum. And how did we do that is shown in this figure here. So this is what we did, the self-consistent library. This is what it does. So in that case, what you have to, you compute the energy that is dumped on the planet from the host star. Then you have to we solve the radiative transfer equation throughout the atmosphere by how much of the energy is absorbed and like different opacities chemistry. So to solve this radiative transfer, you need what's the composition of the atmosphere. So that is we do using we compute using equilibrium chemistry. Then once you know the abundances, you can use the opacities of different species. Now the opacities become very important. Like for Earth or like polar planets, we could use Hytran database, but for hot Jupiters, we have to go to higher temperature like exomole. So most of the opacities that we use are from exomole, and also we have to use hydrogen helium broadening rather than broadening due to the air like that we do for Earth. So all this integrity complications come into this. And we do this iteratively, finally, until we get a pressure temperature structure that is in radiative convective equilibrium under the constraints of conservation of energy and hydrostatic equilibrium. So this is what the ultimate PT profile of the planet will be across different parameter space. So this is what we do for our the self-consistent grid for around 89 hot Jupiter planets, and using this pressure temperature, then we simulate the transmission and emission spectrum of these planets. And this is done for like a recirculation factor so here we were assuming isothermal pressure temperature structure, so we could use a temperature, but when we do it self-consistently, we can't assume a temperature because temperature will be different in different parts of the atmosphere. So what do we do is we use a variable called recirculation factor, in which governs how much energy, because since these planets are tidally locked, the energy will come on the day side and it will be recirculated to the night side. But how much of this will be recirculated, we don't have a handle over that, because we don't know what are the wind speeds. Therefore recirculation factor is one of the variables in the grid. We change it from no recirculation factor, imagine like all the energy just stays on the day side, we don't know how, magically somehow, to and the other point is other grid point is efficient recirculation factor, which means half of the energy that is dumped on the day side goes to the night side. So this has this has implications on the pressure temperature structure as well as the spectrum, which I'll come to that in a minute. How does it affect? And also we also change the metallicity and C2 ratio here to see how does it affect the chemistry, then the pressure temperature structure, and thereby the spectrum. So and like when we were developing this grid, actually one of the very good paper data started coming out. So in our group, this was when I was doing my PhD at the University of Exeter, and the data for WASP 121, which is one of the ultra hot Jupiters, like around 2500 Kelvin, the data started coming from that. And in that, we actually detected, we applied this grid of models to that, and we detected a thermal inversion, like for the first time in an exoplanet atmosphere. And so that we were very excited by that. And that was published in Nature. And so that was very good. You can clearly see here on the right-hand side, the figure. So this is the red color area shows the spectrum. So the data points for WASP 121b. Which is the Hubble spectrum, Hubble WFC3 G141, and it is compared with a brown dwarf spectrum to give what it means to have a thermal inversion in a spectrum. So when you have a thermal inversion, what you will have is you will have a PT profile that looks something like this. It starts lower in the atmosphere, like it decreases, and then it starts increasing, like you can see here. When you have a thermal inversion. So what will happen is when the radiation that is emitted from the lower part of the atmosphere, or maybe in this figure, so this is without thermal inversion, this is with thermal inversion. So without thermal inversion, when the radiation is emitted from the lower part of the atmosphere, it is hotter, and that will give, and it will be absorbed in the upper part of the atmosphere. So you see an absorption feature like this, which we see in many of the brown dwarfs. Absorption, and this is a water absorption feature, it will be absorbed. But if you have a thermal inversion in the atmosphere, the radiation that is emitted lower will be absorbed here, and it will be re-emitted at those layers at a higher temperature. That's why it will be seen as an emission feature that you see here for WASP 121. And this is what we detected for WASP 1. So that confirmed that there is a thermal inversion layer present on the day side of WASP 121. So this is one of the important applications of the grid we did for this planet, and this was an important, interesting discovery. In this way, we applied this library to many different planets in between, and we have made and many different species were detected. We were able to constrain the thermal structure, all this thing, and many could be done in the near future. And one more thing to highlight is like these models are one-dimensional models. We considered a 1D layer of the atmosphere, like a vertical column. Now, but the real planets are 3D in nature. So ideally, you need like general circulation model GCM, but they are very complicated. So what can be done is also you can combine one-dimensional models to get a 3D picture also. Like for transmission spectra, you could combine them linearly. Like you could have one model that is representing the one limb of the atmosphere, and the second model the other limb of the atmosphere, and you can combine them linearly. And this has been shown in the literature that it can represent therefore the 2D nature of the atmosphere. This is what we can do using this library. And then during this development of libraries, one thing that we important do is we do sensitivity analysis, because these models are very complicated. There are many knobs to turn. So how does it affect the spectrum? How does it affect the pressure temperature? So we need to understand it. So that gives us an important understanding of what's happening in the atmosphere. And this is one thing when we notice by developing this self-consistent grid, there is one important opacity so-called H minus, which is quite important in stars. So for ultra hot Jupiters also, we thought this is important. And in last 2-3 years, many papers have been published that showing the importance of this. So what we did is in our when we were developing this library of models, we tested how H minus opacity can affect the pressure temperature structure. So in WASP 121, we know that there is a thermal inversion layer, but we don't know what is causing this thermal inversion layer. Like because if you need a thermal inversion layer, something should heat up the atmosphere. Like on Earth, there is ozone that absorbs the ultraviolet layer and heats. But for WASP 121, we don't know. There are many theories, like there could be titanium oxide or vanadium oxide. There could be other different species. So here what we did, we tested if H minus opacity could cause that. And actually we see H minus opacity has the capability to form strong thermal inversion. And here you can see clearly in the plot, like without H minus opacity, this blue color, there's a very small thermal inversion, but with there's a strong thermal inversion, and therefore we can say that H minus opacity has the potential to form thermal inversions in hot Jupiter planets. And maybe this is the main reason for opacity in many of the hot Jupiter. We don't know, because H minus is quite common in stars, so we think that maybe in hot Jupiter planet this is very common. But how do you find if H minus is there or not? So you can see here the plot on the right hand side, this plot, which shows H minus feature. How does it look in a transmission spectrum? You can clearly see that in the if you just look at the optical part, it is almost like a flat cloud-like feature, resembles a cloud-like feature. So it will be very difficult to differentiate between H minus or cloud just using the optical data. But if you combine that with near infrared data, you can actually detect H minus, because the H minus bound free absorption actually starts decreasing. It goes around 1.6 micron, it just drops off like this. You can see here in the plot, and that is one of the key features you can detect for H minus. And this was just detected last week. The paper was published by the group here at Cornell, where we detected H minus like in a transmission spectrum of an exoplanet in HAT P41b, where we see this structure actually. For H minus. So this is the starting step. Maybe this is more common in many other planets. So this was one of the important results we found by developing this grid. Does anyone have any questions? Or I heard. Is it good? Okay, then I'll just continue, I guess. Is that all right, Suri?
Yep, please continue.
Yeah. So the next one more thing that we tested was the effect of ion opacity. Like, how does the ion opacity affect the pressure temperature structure? So what we found is actually the ion opacity could form secondary inversions. It can't form as strong opacity as H minus opacity because ion is, and the reason is ion has very strong features in the optical, like almost in the UV. Like around 0.3 to 0.4 micron. So ion does not have that strong opacity to form inversions for a planet like WASP 121. But importantly, ion opacity, the capability of ion to form temperature inversions is dependent on the host star type. So if you have a host star that peaks in the ultraviolet, like more hot stars, then it will absorb a lot of opacity because in the optical, and that can form temperature inversions. And we saw that for one of the hottest exoplanets, that is Kelt 9b. And actually in Kelt 9b, in our models, it is part of a grid of models, and we can see that ion can form temperature inversions in Kelt 9b as strong as that formed by H minus or TiO-VO. So that is one of the important findings we saw. And it has, but the problem is detecting ion in transmission spectrum might be a bit tricky because it has very strong features but very narrow, and that too in the ultraviolet and optical side. So it will be difficult with any of the current instruments. But that can be done in high resolution spectroscopy, which people have done recently. So, and like to just give you, like earlier I was talking about like how recirculation factor and metallicity, how this affects the spectrum and the pressure temperature. So this is what I'm showing here. So in this plot, you can see how the recirculation factor affects the pressure temperature structure. So this plot shows temperature and pressure on the x-axis and pressure on the y-axis. And you can see as you increase the recirculation factor, what you are basically doing is as you increase the recirculation factor, you are reducing the energy that goes to the night side of the atmosphere. That's why you see initially the pressure the pressure temperature is non-inverted because it's most of the energy is going to the night side, around 75%. this 0.25, and in the other case you're at 0.5 the 50% of energy is going on to the night side, and like increasing at an point a recirculation factor of 1 means all of the energy just stays on the day side, nothing goes in the night. So that's why it has the highest number. So this is how we vary the recirculation factor, and we see the pressure, temperature, structure changes, and this then directly impacts the emission spectrum. Here you can see that for the cooler recirculation factor 0.25, the emission spectrum, the planetary spectrum. Here what I'm plotting is on the y-axis is the planet spectrum as a function of wavelength. So it's very low, the flux is low, and as you go increase towards the recirculation factor of 1, the pressure, temperature, structure, the temperature increases, and that's why the flux increases, and the amount of flux increases. That is what we see. This has impact on the spectrum, and that this we could easily constrain then on exoplanets when we see and even using, and we are actually using our grade of models with Spitzer. Even with Spitzer you could do that, actually we are seeing that. And then after recirculation factor, then how do you constrain the metallicity? Now in this you can see the metallicity has an interesting effect on the pressure, temperature, structure. So what does metallicity do is metallicity increases the heavy elements in the atmosphere. So what happens is that's why the scale height, the size of the atmosphere decreases. Like if I say the scale height of Earth's atmosphere is like 7 to 8 kilometers, but the scale height of hydrogen helium dominated atmosphere can be thousands of kilometers because of the hydrogen helium. They are very light atmosphere, so they are very big. But Earth's atmosphere is very heavy. So so that is what effect you're seeing here. As you go from low metallicity to high metallicity, you can see the abundances of the species here in this figure. The hydrogen and helium is decreasing, while the abundances of species like water, carbon dioxide, carbon monoxide is increasing. And that is what we see also, like the Jupiter in our planet, in our solar system, or Saturn, they are like hydrogen helium dominated, so they are low mean molecular weight. So while if you go towards Venus, they are like CO2 dominated. Earth is a different case because we have a lot of disequilibrium effect, a lot of oxygen is being pumped up. So that is what, so under equilibrium chemistry, if you increase the metallicity, the atmosphere becomes heavy. Now, if atmosphere becomes heavy, what you are doing is, as you go from this like a lower metallicity to higher metallicity, the size of the atmosphere shrinks. So you are probing higher in the atmosphere. And that is what we are seeing here. With metallicity, you probe in the higher pressure regions of the atmosphere. And this then has implications for like, as I show here, atmospheric, like what are the species you look at, like different species will be dominant, and you're probing different parts of the atmosphere also. So these all things come into the effects of metallicity. And similarly, since I don't have space, I won't talk about effects of C2O ratio, but in C2O ratios, you will also have similar structure. Like the C2O ratio changes the pressure, temperature, structure, and therefore the spectrum. Now, in all this work, we started with equilibrium chemistry, but more work is needed in the future to include disequilibrium chemistry effects. That is because the most of the, especially for colder planets. Now, currently the planets that we are looking are hot Jupiter and warm Neptune because we have observations from them. We don't have many observations for super Earth and sub Neptunes. But as we go for this colder planets, disequilibrium chemistry, which means like taking the effects of vertical mixing, the photochemistry due to the host star radiation, all this will become important. So this effects will include in the next version of the library for colder planets. And then also we need sophisticated treatments of clouds. We can't just use gray cloud decks. We need to go higher, but that will happen only when we get good constraints from the observations, which we hope will happen with JWST. Then a more generalized chemical network is needed to take all the reactions, as Romane talked about here, for proto-planetary disk. And then also one more important thing is for terrestrial planets, we need to also take into account the atmospheric gas flux that comes from the interior model. So it will be good to couple with those kind of models to get a handle over like what gases are expected in a super Earth and sub Neptune planets, and that is how we can then model this planet. So I'll end there and like leave room for any questions if you have. Thank you.
Yay! Any question for Jayesh? I can go first. If anyone doesn't have any immediate question, could you explain more of this plot of effect of metallicity?
Yeah.
The second one, why the methane?
Okay. Yes. So effect of metallicity, the transmission spectrum plot of metallicity, is that?
No, the one before the last one.
Okay. So
why methane
so,
kind of drop down like that?
So as I'm thinking now, atmospheric metallicity. So in the equilibrium chemistry, maybe the methane will be governed by how much carbon is available, and you can see. Now, I'm not a chemistry expert, but I can think like maybe the carbon tends to go towards a more stable molecule, that is like carbon monoxide and carbon dioxide. The carbon tends to go there. So that might reduce the availability of carbon for methane, and that's why its abundance decreases, I guess. That would be my first of
Okay.
the hints. But I might have to think. That's a good question. Yeah. That is one
I
of the
see.
potential reasons, I think.
Robert, do you have a question?
Hi, yeah, very nice talk. So I've got
Thank you.
kind of two questions. So the first one relates to the opacities that you present and calculate for the for this work. So
Yes.
kind of, how do you decide on the actual molecular opacities that you use there? Because I know it wasn't mentioned in this talk, but I checked the publication, and it appears like some of them, well, many of them have like since been updated in like maybe even like the last decade. So I would say some of them are slightly out of date at the moment. So how have you chosen the particular opacities that you've used?
Okay. So one important thing, the opacities are governed by the chemistry. So when we run the equilibrium chemistry, we know like for a particular pressure temperature structure that we expect for hot Jupiter planets, which molecules will be abundant, like H2O, CO2, these all particular molecules will be abundant. So this gives us handle over like these molecules are particularly abundant. So we should definitely include the opacities for those species.
Okay, sorry, I maybe misspoke there. I meant, sorry, how do you decide on the line lists that go into these opacities? Because some of the line lists have been, so some of the, like, for example, you know, the high temp line lists have been updated. There's a number of exomol updates since the ones presented. So is this just because of, is this like some code that has not yet been updated, or is there a reason for picking those particular line lists?
Oh no, so this all the opacities that we use in this codes are updated ones. These are the most recent ones. So all the opacities that we use are from exomol, most of them. Only some of them will be from Hytran, like for which exomol did not have 2-3 years ago. So this code was like as we started developing around like 2014. So since then we have been adding. So most of the species like water opacity we used BT2, that is the exomol line list. Then VO opacity comes from VOMT. Most of this is from exomol. Yeah, most of the opacities are from exomol.
Yeah, so I appreciate it's not like some of the updates have been like fairly recent, but since then there have been, so even in 2014 some of these line lists would not necessarily be up to date. So I would just suggest maybe recheck the recommended line list for some of these molecules, because
yeah, that's a good point. Yeah.
Okay. And then I was going to say, yeah, well, basically the second part was, are these recalculated on like a, you know, for example, when you get a new line list, do you recalculate the opacities, or are these now like a fixed in time? Like
no, we do that. We actually recalculate. So as soon as like the new opacities come in, generally, of course, there will be a lag of like 4 to 5 months. So, but we do that with the new line list. Like anything that comes in the exomol, then we have to compute the absorption cross section with hydrogen, helium, atmosphere broadening, and all those things taken into account. So we have to compute that. And if we go for like higher metallicity, also we have to start taking account the broadening it to different other species. So that's why we have developed that at the side code to keep that to include in this models. Yeah, we do that.
Yeah. Okay. Well, yeah. So yeah, just to reiterate then. So some of these have been updated, and the high temp, for example, have been updated, particularly for methane, which may be
yes, I have to include that.
Useful.
I know, I have heard about that. Yeah, thanks.
And we're also including a number of hydrogen helium broadening, which may be slightly different to what you're using. And on top of that, there's the partition functions, which I think probably could be updated.
Oh, okay. That will be very helpful. Thanks for that.
Yeah, no problem.
All right. Any last question for Jayesh? Okay, I don't see any hands anymore. So I guess we will just stop here as we're running out of time too. Thank you everyone for coming, and we see you in 2 weeks. If you want to hang around to talk to the speaker, please do so. Otherwise, see you later.
Thank you very much, everyone.